4-bit synchronous counter. In the previous session, we have seen 3-bit synchronous counter. Now in this session, we will see 4-bit synchronous counter. For implementing this 4-bit synchronous counter, the first step is identifying the number of flip-flops. So in the name itself, it is saying that 4-bit counter. So for implementing 4 bits, we required 4 flip-flops. So that is over. Next step, state diagram. So here for 4 flip-flops, the 4 outputs starting value is, for example, consider 0, 0, 0. If all the outputs are 0, then the combined value, the weight of the counter is 0. The next state, after 0, next count is 1, next count is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these counts will done by for every clock cycle, for every clock pulse. So for each and every clock pulse, the count is going to up from 0 to 15. After 15, next count is 0. Why? Because we have availability of 4 flip-flops. We don't have any availability of 5th and 6th flip-flop. So for that reason, the count is going to repeat here. So see here, the next step, excitation table. In the excitation table, present state Q3, Q2, Q1, Q0. Right? So this is Q3, not Q2. Right. So we are using 4 flip-flops. So here the present state Q3, Q2, Q1, Q0, and next state Q3, Q2, Q1, Q0, and the inputs T3, T2, T1, T0. So if the present state is 0, next state 1. If the present state is 1, next state is 2. If the present state is 2, next state is 3. Like that, you have to draw the truth table. Then see here, present state, next state. Based on the present state and next state, you have to analyze what is the input. If there is no change in the outputs, then T3 is equal to 0. So like that, you have to check for all the combination. Then you will get this inputs table, that is T3, T2, T1, T0 table. Then identify what is T3. T3 is equal to sigma small m of 7, 15. Then what about T2? That is sigma small m of 3, 7, next 11, next 15. So this is the T2. Next T1, next T0. Like that, you have to, you will get the equation. You will get the Boolean functions. So the next step is applying the Karnaugh map and identifying the simplified Boolean expressions. So here T3 is equal to 7, 15. I have made a 4 variable K-map here, and from this 4 variable K-map, I represented the 7 and 15 blocks here, and I made a group. From this group, what is the equation we will get here? See, for T3, what is the equation? Here, the common variable in this side Q2, this side Q1, Q0. That is Q2, Q1, Q0. That is the T3. That is the T3. So see here. So this is the T3. Okay, so T3 is equal to Q2, Q1, Q0. What we got from this Karnaugh map, the same Boolean function we represented here. Next T2. T2 is nothing but as 3, 7, 11, 15. 3, 7, 11, 15. Now from this, the common values are Q1, Q0. So Q1, Q0 is the T2. In the same way, T1 is equal to Q0. So see here, from the entire, this 8 squares, we will get the function Q0. Why? Because Q2, Q3 and Q2 is completely varying here, and Q1, Q0, in this Q1, Q0, Q1 is varying. Why? Because here Q1 is bar and Q1 is here original. So in the Q0 value, there is no change. So for that reason, this is the answer Q0. And coming to T0, all the functions are involved here. So all 16 variables we have mapped here, and the final answer is 1. So like that, you have to analyze the 4 input expressions. Simplified Boolean. Next, so the logic diagram. Last step. In this 4-bit synchronous counters, up counter, T3, T2, T1, T0. That is 4 equations we have written here. We have written here. Next, so first we have drawn 4 flip-flops here. We have drawn 4 flip-flops here. That is T0, T1, T2, T3, and we have given clock signal also.
Mama, please, Mama.
Some of the students, they have to mute their audio. Right. So based on these functions, you have to draw the remaining circuitry. That is T0, you have to keep 1. T1, you have to connect like this, right? So in the same way, here T0 is equal to 1 and T1 is equal to, you have to connect to the Q0, and T2, you have to make an AND gate here, and you have to take Q1 and you have to take Q0, and the output of this one you have to connect here T2, and T3 is equal to, this is also we have to connect one AND gate. That is, one is Q2, Q2 I have connected. Next, for T3, Q2 I have connected, Q1, Q0. Q1, Q0 is nothing but as T2. So the output of this AND gate you can connect directly. You can connect directly. Why? Because the AND gate output is nothing but as Q1, Q0. Otherwise, if you can connect like this. Otherwise, if you're not interested, you can connect like this also. Take Q1 signal and Q0 signals. These 3 signals you can connect in this fashion. Okay, that we will see now. So these are the connectivities for 4-bit synchronous up counter. For 4-bit synchronous up counter, these are the connectivities. These are the connectivities. So this is the design of 4-bit synchronous up counter.